Okay, so recording now. I missed the steps on pre-processing, but if you want to see more about pre-processing, you can just view the notes if you're watching this lecture later. Okay, so where we left off, we're talking about assembly. So the way to actually assemble your code, you can use the, I think it's AS? Yeah, the assembler is the GNU assembler. So the way we can do this is to say AS -o hello.s and then hello.i. What this will do is take in the hello.i file that we had saw before and assemble it, convert it to assembly code. And you can see right here, well, let me actually fix that hello file. I had added more content here. Let me remove this. Put it back to where it was before. And then cpp hello.c, or gcc-e, I should say. Hello.c, and then direct that to hello.i. Hello.i, yeah, that seems to be correct. Now we can say as hello.i -o hello.s. All right, let's see. Might have ran into a small mistake here. What did I do wrong? Oops. Oh, gcc-s, okay. So we're not going to invoke the assembler directly. We're going to invoke it through GCC, which probably does extra steps that I am forgetting about. So GCC hello.i -o hello.s. So here we can actually invoke the assembler from GCC with the -s flag, capital S. And now what we can do, we'll open this in the bottom, is actually check out the contents of that file. So hello.s. We can see this is the assembled output. I believe this is x86-64 AT&T syntax assembly is what we have here. So there's all these different flavors of assembly. If you took computer architecture, you probably are familiar with MIPS. The one we'll be using in this course is x86-64 AT&T syntax assembly. So yeah, you can see all this code here. Assembly is like the highest level, well, lowest level, high level programming language you want to use in any kind of programming endeavor. Typically these days we don't use assembly for actually writing code by hand because assembly is not a structured programming language. We don't have access to nice features like if statements and while loops and other structured forms of programming. You don't see any braces in here. The most structure we have are these labels, but that's not really structured programming. But it's still English text with some numbers and a few special characters like this % sign, for instance. So we can kind of read it, so you could write it by hand, but you generally don't want to. I guess one notable recent example, not that recent, but one notable example of somebody who actually did use assembly to create some program was this guy, I think it was Chris Sawyer. He made the game Roller Coaster Tycoon, all in assembly, just so it can be very fast. Kind of funny if you're just curious about like somebody who actually used assembly for some like actual purpose in fairly recent times. That's like one notable example. But these days, people typically just use C code at the lowest for writing fast code. So I guess one question here is, do we think the CPU runs this directly, this assembly code? No, right? So if I were to split my screen here and use hexdump, so do we remember what hexdump does? Yeah, exactly. Exactly. If we run this on the hello.s file here, we can see all this hexadecimal code on the left, this binary code, hexadecimal representation. And then on the right here we have all of this the ASCII encoding or the decoding of this code on the left here. Yeah.
About the roller coaster tycoon example, would someone doing that today notice the same performance gains? Like
if they were very good at programming and they could actually write code faster than a compiler could, like more performant code than a compiler could produce, then yes. But it's harder and harder to do that these days because compilers are very smart, and like GCC and Clang are optimizing compilers. They write code to be as fast as possible. So they're very good at writing optimizations that people may not even think of. So it's possible, but you have to be very good at what you're doing. Yeah, that's not a reason not to try, though. So for instance here, we see this call instruction on the right. Now, this call instruction on the right, the bytes that correspond to it on the left here, these bytes correspond to the ASCII representation of this sequence of characters, CALL. This is not, again, to reiterate, this is not the byte sequence that corresponds to the actual call instruction that your CPU can recognize and actually execute. So to actually convert this assembly code to a form that our CPU can recognize, we have to do another step, which is, actually I got this backwards. The assembler is what converts the preprocessed code or the assembly code to object code. The compiler is what converts the assembly code or the source code to assembly. That's why we use GCC to convert the assembly code to the source code to assembly. So again, just to reiterate, we had used GCC to convert the preprocessed code to assembly, and now we're going to use the assembler. Sometimes you get these terms confused because they're very similar. Now we're going to actually use the assembler to convert this hello.s file to an object file. So I think, let me see, I have this all in my notes here. So we want to use, we'll use the assembler directly here. So now what this will do is convert the assembly code that we just saw. So here's that assembly code we just saw. This will convert that assembly code to an object file, which an object file is binary code that is prepared for running, binary code for running on your CPU, but is not necessarily ready to be run on your CPU by itself. So to maybe show you more of what's in this file, we can use a utility called object dump. And actually, before I even do that, if we try to open this file using just like a text editor like Vim, you'll see that it's really unintelligible. That's because everything in here, for the most part, is again binary code, not meant to be read or interpreted by humans. There are a few strings in here that you can see are legible, like the hello world string. That's because they're actually stored in the binary as a string. So we can read them in our editor. But if we wanted to actually see what instructions are stored in this binary, we can use a utility called object dump to do this with the -d flag. That stands for disassemble or convert the binary code back to the mnemonics, the human readable form for us to interpret. So I can say object dump -d hello.o, and here we can see the actual disassembled code here for that binary. So one more thing to point out that we can also do here is use the -t flag to get a symbol table from this binary as well. And a symbol table, also called a linkage table sometimes, contains all the symbols that are in this file. A symbol is, among other things, this includes function names. So we can just focus on function names for now. It also includes global variables and whatnot. But we'll just focus on function names that are going to be in the symbol table. And it also tells you where they are defined in your program. Now, if we look here, we can see that main is defined in the .text section of our program. That makes sense. That's where code should be stored, the .text section of a assembly code. But the puts function, which I believe is what the printf function turns into. I'll just change it for puts just so we can be clear there's no ambiguity here. Puts just prints a given string with a new line character at the end. That's all puts does. And it doesn't accept formatting. So if you just want to print a string with a new line character at the end for you, you just use puts. So I'll rerun the steps we saw before. So gcc-e, rerun that one, gcc-s, rerun that step, and then rerun the assembly. And now we'll run the object dump again, -t,
I don't know if you said this already, but could you put all the steps that you're doing right now into a makefile, or is that not?
You could. You wouldn't need to though, typically, because GCC does all this for you when you run GCC by default. It runs all of these steps except for loading for you when you pass just a single program name to GCC. So typically you wouldn't have to write all these steps in such granular detail, but today's lecture is kind of introducing you to the overall concepts of what's going on under the hood when you run a compiler. Because in the rest of this course, we're going to be writing our own compiler. So, all right, so let's just see the, oh yeah.
Is there any way to see the actual sequence of binary out of the object file?
Of the object file, see the actual binary?
Yeah.
I mean, you can just open it in, well, I guess hex dump. I think that would work. Hello.o, and yeah, we can see the actual byte sequences But typically, what you would want to do, especially if you're doing like, I don't know, like binary analysis, you'd use a tool like ObjectDump, or even like readelf is another one for executable linker files. But we'll just focus on ObjectDump for now. So ObjectDump -d hello.om, you can see the disassembled output. Yeah.
Did it omit the studio image part of the code?
Yeah, so this is just the .text this is just the .text section that we wrote. And there's actually a reason why that's omitted. It's not actually omitted, it's more like it's not included in our actual compile binary. And I'll explain more of that in a second, but that's a very good question. We're using an approach, I'm going to explain this more shortly, but we're using an approach right now by default known as dynamic linking, which means that code that we want to include from the standard library is actually not in our binary. Our binary actually, or the loader actually looks this stuff up for us and includes it from a file, in a shared object file in our machine when the program starts running. But there is a way to actually statically link this information into our binary itself, and then it will be available for viewing in the object file as well. But I'll explain more of that later. But that's a good question. Yeah. Okay. So if we specify -t here, you can see that putS function that this is sort of related to that point, that we are calling in this hello.c file. So again, hello.c, you can see we call putS. For the location, it's listed as UND, which means undefined. So even though we're calling this putS function, and we can assumedly run this program, if I were to run gcc hello-o hello.c-o hello, and then run hello, you can see that it actually does run and works. So why is it that putS is undefined in the object file? I'll explain shortly, but you can guess if you want to give a guess.
Oh, is it because of the includes?
Sort of. No, not quite. Not quite. Includes are like a similar concept, but it's not quite the same thing. So includes only provide declarations of functions that we want to call. They don't provide the definitions. The definitions are present somewhere else in this tool chain, or we get them from another part of this tool chain, which I'll explain now, which is linking. This is the last proper step of compilation. So linking, among other things, resolves references between different files. It resolves references to symbols, including function names. So it looks up in your system where the definitions of those functions are, and depending on how you compile your program, it will use information that might be embedded in the binary to do that lookup, to find out where those files are. So this is like, the steps to actually do this are a bit more complex than the previous steps, so I'm going to have to refer to some notes here. But if we go to my script that I have here, okay, I'll copy this. Okay, so this is the command to actually run the linker. I know it's named LD, it seems like this is called the loader, but that's kind of a misnomer, it's the linker. Where we're actually going to resolve the references between our main, or our compiled hello.o file with several other files that are necessary for it to run. So the first one we're linking it with is going to be the cruntime1.o file. This includes some setup code for setting up the main function. The libc.so file. This includes the definitions of libc functions like putS. This is where putS is going to be actually defined in this shared object file, so. We're also passing to the linker our object file itself, the one that we want to compile. And then we're specifying explicitly where the dynamic linker binary is. So this is actually a program you can run to actually execute some binary code and have the dependencies resolved when it goes to run. And we're actually specifying manually here in the command line where that linker is. And finally, we're specifying the output name is just hello. Yeah.
Is this linking like similar to the one that you did early on with class with the different files?
Yes, the different .o files. Yes, except, so GCC was sort of abstracting away some of these extra commands that I'm specifying here. Like GCC will automatically add link with CRT1. It will automatically link with libc.so. Here we're doing all that manually, just so you can see exactly what's going on when you try to link a file. So if we run this, it seems to run successfully, and now we can actually run hello world, and it works. So this is everything that's actually going on under the hood when you go to compile a C program. Well, maybe not everything, but usually this is what's going on. Okay, so one more thing I want to point out here is that you'll see that in this hello.o file, when we look at the assembled output, it says ELF64 x86-64. So ELF stands for executable linker file. These are files that can be passed to a linker and are also executable. You can try to execute them at least. And the x86-64, well, that refers to the machine's architecture. So if I run uname-p here, so this uname gives you system information, -p specifies give me information about the processor. You'll see that it actually says that I'm on an x86-64 processor. So one thing to note about compilation is that when you compile a program, it is always going to be for a specific architecture, specific platform. So I'll talk more about this in another lecture, but back in the old days, whenever you had a programming language, you had to create a separate compiler for each target platform you wanted to target with that language. So if I had, if people invented, let me think of an example. The C programming language, if you wanted it to work on Mac and Windows, you had to create a compiler for C to Mac and a compiler for C to Windows. So it's like an M by N problem. And then if you had a new language, like let's say, I don't know, C++, you had to create a new compiler for C++ to Windows, C++ to Java, or C++ to Mac, I should say. So you'd have like M times N, M number of languages, N number of targets. You have to multiply both of those to get the number of total compilers you would need. That's a lot of duplicate work. And I won't go into this in this lecture, but there are ways that have been recently invented, like in the past 10 years, to make that an M plus N problem, where you only need to create really one, using an intermediate representation, you can just circumvent having to create a separate compiler for each language and target. Yeah.
So this is a really short question, but is that still present today with ARM then, or is that a whole different thing?
ARM is a different architecture, so yeah,
that's-
exactly.
Okay.
But not really. It's not an M by N problem. You only have to write, as long as you can compile to an intermediate representation, you can go from there to any of the other targets, which I'll explain more about that in another lecture. But yeah,
Don't want me to jump ahead either, but isn't that the problem that the JVM is supposed to solve?
yes. So JVM is an example. The JVM is like kind of interpreted. So, but yeah, that is an example of how you could solve that problem with the JVM approaches. So the Java Virtual Machine sort of solves that problem by having a middleman exist between all these different targets that you're trying to run your code on. The Java Virtual Machine is what actually runs your code, your Java code when it's compiled. Okay, so what we did in this example was use the loader to perform, or the linker to perform what's known as, to link our program using dynamic linking. But there's another kind of linking that exists, which is called static linking. So let me see if let me just make sure that I'm not getting too far ahead here in my notes. Okay, yeah, we're good. So I'm going to have to open my notes here for this one because this is another really long command. Yeah, I'll copy all these. So we'll run these three commands again. I'll remove the hello binary. All right, and so now in this example, what we're going to do, now this kind of answers your question before, why didn't we see the standard I/O code in our object file? That's because our code was dynamically linked, which means that the references to all the functions defined in standard I/O were resolved when the program was about to start by the loader. But here what we're going to do instead is perform static linking. We're actually going to compile all that code that's in standard I/O, not standard I/O.h, but in libc.so, the actual definitions, file defining definitions of the standard C library. We're going to compile all that into our actual binary, our compiled output. So here we specify with the dash static flag we're going to be using static compilation, or static linking I should say. We're specifying the output file to be hello. And then here we're specifying all the files we need to enable our program to run correctly. And I won't go into the details of this too much, but the big idea is that these are all setup files. These files are all compiled to initialize main, set up some variables, and include some symbols that main needs to run. These files actually include some functions that GCC compiled code expects to exist for program execution. Here's we have libc.a. So .a means archive files. They are compiled, precompiled binaries that contain definitions of functions and whatnot. So this libc.a file contains precompiled definitions of the libc functions. This is where puts is going to be defined for us in this case. And then these last functions here are teardown functions. They deconstruct some parts of your code and then clean up stuff after main is done running. And they actually call exit for you to get the correct return value back to the user. So if we were to run this, now it seems like nothing went wrong. And if we run hello, we get hello world as before. But there is a difference. And this difference is sort of just beneath the surface. If we run object dump on hello now, you can see it's way longer than the last one was. Because now we've statically compiled all of the code that was in libc.a into our binary. Yeah.
This is kind of like a question, but like, what is the like main like difference in utility between the two?
No, that's a good question. I was actually going to get to that. So very good question. So the question is, why would you prefer static linking over dynamic linking? Well, there's a few different reasons. Number one, static linking makes your code a bit more portable in the sense that if you statically compile everything into the binary, you can just give you can just send your binary to someone else, and as long as they're on the same architecture as you, it'll just work because everything the program needs to run is in that one binary. Whereas with the dynamic linking, they need to have the correct object files or archive files and shared object files already installed in their machines. I don't know if any of you have ever used like the game platform Steam before. You might notice when you go to start a video game on there, you have to download all these different files before the game runs. It's downloading shared object files, which on Windows are called, I think, .dll files, dynamically linked libraries. So that's like one example of where you might see something like that occur. Now that's only because you're using dynamic linking, do you have to pre-download those files. But the downside is that because if you use static linking, your binary is going to be huge because you're compiling all this code which already exists somewhere else in your machine. You're duplicating it and recompiling it into another binary. So if memory is a concern, actual like storage space memory in your disk, then maybe don't use static linking. Static linking can also sort of help with speed because if everything's in one binary, it can make your code a little bit faster just at startup. Whereas with dynamic linking, you have to resolve references to all the functions and whatnot by actually looking in your library path to actually find where all these functions are defined, which library path is like another environment variable. I think I can echo this here. No, it may not be defined here, but yeah, that's another thing. The loader needs to look up where all these functions are defined when your program goes to run. So it'll take a little bit longer to run at startup because of that. So that's just some of the examples, like the differences between static and dynamic linking. You can look all this up. There's also, I think, like weird legal differences between the two. Like if you compile a code using static linking, there are some like legal problems you can encounter if you're depending on the licenses used with the different with the code that you're statically linking against. Yeah, so. So that all being said, if we run object dump -t on hello here, do we think putS is going to be undefined still? No, right? So it's a lot of code. So let's grep through this. PutS, we can see putS is defined right here in the .text section, which is where code lies in a assembly file. Yeah.
What is the like star ABS star location?
So I'm actually not sure what that is. You'll have to look that up. Yeah, I don't know all the output of this, unfortunately. Yeah. It's a good question though. Yeah.
That's where all the .o files are.
All the .o files are in ABS. Interesting. That's a good point. Maybe it'll tell us if we look at the man pages for object dump. Maybe not. It might be in a different man page. We can just check. So absolute is what it says. is not connected with any section, so I guess it's defined in an object file. I don't really know what they mean by absolute here. And then UND, undefined. Yeah, referenced, but it's not defined there. Yeah. So you can read more about that on your own time. But yeah. Yeah, and the final step here is the loader. So the loader actually runs our code. It's what will actually look up the references to any dynamically linked libraries, so shared object files, or the extension. SO is the extension on Linux. DLL is the extension on Windows for these dynamically linked libraries. And then we'll actually link them against your program in order to run it. So as I mentioned before, let me go back to the script I had up here, the intro script here. Let's perform dynamic linking again. So we're going to run the commands to do dynamic linking. Now, if I actually take this path to the dynamic linker and I paste it in here and then pass hello, it should, there we go. It actually is able to run our program. So the dynamic linker here is actually what's sort of the interpreter for our C code. It's what's looking up those references and resolving them before our program runs. Now, by default, let me see if I can open this again. When you run GCC, this dynamic linker, the one that I listed here explicitly, is the default one that's given to your programs when you compile them with GCC. So that's why you can just run your programs with /hello in this case. It's encoded, it's embedded into the binary. That's the default interpreter for looking up resolving their references. So you don't have to specify this in the command line. You can just run them and it just works. Okay, so any questions before we proceed? And you won't be tested on all these different flags, these different arguments. What you should know, the key takeaway here, is what the different phases of compilation are and what they achieve. You don't necessarily need to know, you won't be asked to run commands to actually execute any of these specific phases, but you should know what these phases are and what they do. Yeah.
When we're making our own compiler, do we have to choose a specific type of like dynamic or static, or could we use it for like different facets of a compiler?
So that depends on what it depends how much of this tool chain you're trying to implement with your compiler. So for us, we're only going to be implementing the compilation proper in our compiler project. We're only going to convert some source language, not .i files, but another language that we've invented for this course that's pretty simple. We're going to be converting language written in that, or code written in that language, into assembly code. That's all we're doing. So linking is still not something we're responsible for. You'll be using, if you want to actually run your code, you're going to have to use existing linkers to do that, or you can just use GCC, which can actually link code for you and automatically include the C runtime, the libc, shared object file, all of that. GCC can do that for you if you use it for linking. And we'll actually see later in this course with our compilers, well, I'll explain this more in more detail later, but we're actually going to be able to compile and link code we write with C code and actually have them interact with each other. So to answer your question, whether or not you tackle linking is up to you. That's why these are all separate parts of the tool chain. If you're implementing just a compiler, that's a different part of the tool chain than linking, so you wouldn't have to implement it. But some languages do choose to tackle linking as well. I think the Go programming language has all of its code be statically linked, I think. Or maybe static linking is just the default. Yeah.
I think it's just the default.
Yeah, there has to be a way to do it dynamically. Yeah, but I think static is just the default. Yeah. Okay, so I hope that was pretty comprehensive. Hopefully not too confusing. But again, big idea is just what these phases are, what they each do. That's the key takeaway. So I think now might be a good time to take attendance. So I'll put the attendance sheet here if you need to take physical attendance. We can take a few minutes break. I'll put up the UCF here now and pause recording. Okay, so we're back. Now I want to talk about separate compilation. So I think I talked about this earlier in this course, separate compilation. Does anyone remember what this refers to?
It's the result is the .o files, isn't it? So you compile two C files.
Yeah, the idea of separate compilation is that you compile two files separately and then link them together to form a final executable binary. This is better than writing all your code in one place because it means you can change one part of your code and only have to recompile the part of the code that you changed instead of having to recompile everything. You'll still need to relink everything in the end to form the final executable, but you don't have to recompile everything each time. So let's see an example. Yeah, we'll look at an example of this. I'm going to try changing my prompt again. Hopefully this doesn't mess with my terminal output. Okay. I'll make clean. I have a make file defined here for deleting all those auxiliary files that we created. So I'll delete those. And what I want to focus on now for this example are two files, main.c and f.c. So I'll open main.c here. Then I'll make a new window below and open, let's say test. Actually, what I want to do is open this on the right and open this below here, f.c. All right. So in main.c, we have this, let me delete this declaration here actually. We are calling in main the function printf, and we're saying we're going to printf g. The result of g is some number. The function g returns the value f, and then in parentheses 2. So we're calling some function f. In the file f.c, we actually define f as returning x times 2. So if we are to run this program, gcc main.c, we'll just call it main. We'll pass main.c, and we need the other object file, other source file here, f.c as well. And my terminal is doing that issue again. Here we go. f.c, passing them both to the compiler. We'll get a warning saying that there's an implicit declaration of f, but we can actually ignore that and actually still run the main function, and it will still work. So the result of g is going to be f of 2. F returns the given number times 2. 2 times 2 is 4, so we get g is 4. Okay, so now what I want to do is, well, I guess ask a question. If I were to compile, I have some scripts here for doing this, these two C source files separately, yeah, there we go. So we have f.s and main.s. Do we think that f is defined in main.s? No, right? Because main.c doesn't contain the definition of f anywhere. We can see in here, we do have a call to f. I'm not really sure what PLT stands for. I didn't have time to prepare for that before this lecture, but we're basically calling the function f. Now meanwhile, in f.c, or f.s I should say, we can see that f is actually defined right here. We have this label f, and beneath this is actually the whole definition of f, the assembly code defining the definition of the function f. Let me open my notes here again for the separate compilation. So now we can actually compile these two assembly files to object files as we saw before. And if I were to run object dump, I think this is the next command here. Yeah, object dump on main.o, do we think the definition of f is going to be listed as defined in main.o? No, right? It shouldn't be. And if we see here, we actually check, we can see here that f is indeed listed as undefined, UND for the function f. Now meanwhile, if we do this again on f.o, we can see that f is in fact defined here. So we could include f.c. Typically, you don't want to include C files unless you're doing, some situations you do, but usually you don't want to include C files in C programs. But that kind of leads me to my next point, what you're asking about. So you'll notice that what we had earlier, separate compilation right here, yeah. This works without any errors running GCC like this. Well, place that command in again. GCC f.o main.o -o main. This works and we can run main, and it actually compiles and runs successfully. But if we were to try and run just GCC, and as you might have saw earlier, main, main.c, f.c, if we run this, we get this warning of an implicit declaration error, or warning. But our code still works. Can anyone kind of guess why we get this warning from GCC? Yeah.
Does GCC not, I guess, know that we are?
So you're kind of getting to the right idea, yeah?
Could it be because you listed main first, so it's been run and main is a file, or is it?
So that's close.
Is it because of the dynamic
Not really.
linking?
Not really the dynamic linking. Not really related to that. That would be an issue we would encounter at runtime, I think, if that was the case. Yeah.
Because f.c is not used in main.c?
It's not declared in main.c.
Declared, yeah.
So here, when remember, subset compilation, first we have actually compiling our C code to assembly code. And we're getting this warning, actually, if we were to run this again, just on main.c, or actually I guess we could, well, this is where we get the warning. Only if we try to compile main.c to assembly, we get this issue. Let me actually fix this. I specified the out file wrong. There we go. Okay. The reason for this is because the first thing that GCC goes to do when it goes to actually compile code is parse it. Just as we reviewed parsing before with shell programs, it's parsing this code and it's trying to figure out at runtime, or at compile time I should say, look for any potential errors in your code, and it finds that this function you defined, or you're calling f, hasn't even been declared. So the compiler doesn't know what return types, what argument types to expect for the function f. So this is actually just a warning given by the compiler during compilation, during this phase only. This is not concerned with assembly, with object files, with executable files, with none of these other steps, assembly, linkage, loading, none of that is this error concerned with. Really, this error is only dealing with compilation on its own. So we can suppress this error or remove it by just simply declaring f in our main file. And now the error goes away. Because the compiler knows when it sees this function, this call to the function f here, it knows what arguments and return type to expect with the function f. The definition is not important because the definition will be provided during linking. That's why the code is able, that's why earlier when we had this issue, we were still able to compile and run our main binary, even though we didn't declare or define it in main, because ultimately the definition got linked into the binary when we ran GCC here at the bottom to compile these two object files together. So yeah. And now if we were to actually run object dump here, -t on main, it'll be a lot of different functions because we're linking against glibc as well, CRT. But I think f should be in here as well. So yeah, right here, f. In the full binary where we linked main and f.c and f together, these two files on the left here are both linked together. We can see on the right that the definition of f is actually included in the final binary that links those two files together. Okay, so I guess maybe one thing worth mentioning here, I believe this would be an error if I were to try and call f twice. I guess not. Okay, as long as it's consistent. Okay, well, let's get that example then. Can't really think about how to do that one. Okay, this is actually something that's more important that I should probably talk about first. So, if we look back at the disassembled output of the compile binary here, or the assembly code, I should say. So object dump, this would be -d, or no, this would be the assembly code, I think. This would be main.c or main.s. Not here. Where was it? It was in, maybe it's object dump -d main. Yeah, it's somewhere in here. There we go. All right. So one more thing I want to point out is that part of linking, when we're linking with the C runtime, one of the things that that does is add this underscore start symbol to our program, to our compile binary. And as we'll be seeing when we write our own compiler, this underscore start symbol is the actual entry point for your program that the loader looks for. By convention on Linux, the loader does not look for main as a starting point. It looks for this underscore start function, which does some setup stuff, like setting up the arguments like argv and argc and environment variables. It sets some of that up for main, and then it actually calls the main function. So you'll notice in compile binaries, underscore start is the true entry point to your programs, not the main function. And this is given to you by the C runtime. So specifically, that would be, if I go back to my example here, intro.sh script, crt1.0, this file is the one that actually includes the underscore start symbol that the loader will look for. Okay, let's see, so what's next? Yeah, so one more thing I want to point out is this notion of application binary interface. I know it's a long phrase, but we'll be using this repeatedly throughout the rest of the semester. It's very important for compilation. So an application binary interface tells you how, what the calling conventions are for setting up and tearing down function calls in assembly code. So as an example, I guess maybe to get this point across, in our C code, we can actually call functions by specifying them as arguments in parentheses here. So for instance, to call f, we just put 2 in parentheses after f. So in C code, we can actually call functions pretty directly and pass arguments to them pretty clearly with this syntax. But if I were to go into the object dump output here, I'll close these 2 windows. I think we don't need them open right now. Object dump -d main. We'll see that in these function calls that are present in this program, calls to all these different functions here. Maybe I can grep for call. There we go. Yeah, call to the function f, for instance. There's no arguments being passed in this same line of code in the actual assembly code for f. Actually, I can probably open the assembly output for this here. We can actually find it more easily. Yeah, right here. When we're calling g, for instance, in the main file, there's no arguments being passed through directly to g. Not obviously to us, not in the same syntax as for C code, where we use the parentheses and whatnot. So again, just to reiterate here. This call to G, or maybe I should focus on the call to F because it has an argument. This call to F, which is defined in a different file, but the call to F here on the left does not look the same as the call to F here on the right. We're not passing the arguments 2 directly to the call to F. The way that we set up these arguments is through other assembly instructions, which are probably occurring here in the previous lines of code. So right here, we're moving the value 2 into some register, the EDI register. Now we'll see more of this in detail in later lectures, but the big idea here is that we're setting up the arguments for this subsequent call to F on this line of code. And the way that you're supposed to do this, the specific procedure you're supposed to follow for setting up these arguments is given to you by the application binary interface, or ABI, of the system you are targeting. So we're going to be using the system v, system 5 ABI for this course. And that tells us how callers and callees should, and by callers I mean the functions that are calling other functions, and callees I mean the functions that are being called, how they should what they should do in setting up and tearing down function calls. So we'll see way more examples of this later on in this course, and by the end of this course, you should know how to actually set up and tear down these function calls, follow an ABI to actually compile code to assembly that it works for like running on x86 64 machines. And by following, the really cool thing is that by following this ABI, if you can write a compiler that successfully follows it correctly, then your assembled code can be compiled and linked with code that was assembled that was compiled from a different programming language. So by following this ABI, the code that we actually write a compiler for can be compiled with C code that we didn't necessarily write, and the resulting binary can actually run successfully. This is what enables us, the code that we write in our simple IR programming language we're going to be working with, to actually compile and link with C code. So I guess to have this on a slide with more details, what ABI includes, the big idea is calling conventions. Calling conventions and stack frame layout. These are the two things that you really want to take away from the ABI. And I'll give it an illustration of a stack frame very shortly to see what that is. It's basically the segment in memory in RAM where each function call has for managing local variables and whatnot. Yeah, how to pass parameters, how to return different values. The ABI specifies all of this. And to give a great example here, all right, we'll just go to this page. So this blog post is from a guy, Eli Bendersky, or Bendersky, I don't know how to pronounce his last name. He is a Google employee. I don't know if he still works there. I think he does. He has this great blog post breaking down the stack layout on x86 64 machines. And I think this illustration really helps sum up how it works. So you can see in this example, he has defined this function, myfunc, and it has 1, 2, 3, 4, 5, 6, 7, 8 different arguments. They're all long integer types. That specifies, I think, a minimum of 32-bit width for long. I'm not sure exactly what the sizes are there on that. And all this function does is declare some local variables, xx, yy, zz, and then assign them to the results of some arithmetic, and for zz, a function call. What these values are assigned to isn't really that important for what we're talking about today. What's more important is this illustration here, this stack frame. So a stack frame, also called an activation record, is a segment in memory, in RAM, that is located for each call to a function. Each function has its own stack frame. And this enables us to do things like have recursive functions, because if each function has its own layout and its own piece of memory, then we can actually have these different function calls interact with each other and not have them overwrite each other's contents. So what the ABI specifies for us, among other things, is how these arguments are passed in the stack frame. You can see that in this case, following the System V ABI, the first 1, 2, 3, 4, 5, 6 arguments are actually not passed on the stack at all. They're actually passed in registers. So these values here are registers. Registers are small, very fast to access pieces of hardware on your CPU. Subsequent arguments after the first 6 are pushed onto the stack. That's why they're here at these offsets. Well, again, we're going to see more of this much later. The return address is also pushed onto the stack. The base pointer, RBP, that's a special register that stores the base address of the current stack frame you're working in. And then these negative offsets store the locations of local variables in memory. And you'll notice that all these locations are at widths of 8 bytes each. That's because we're working on a 64-bit machine. So 8 bytes, 8 bits in a byte, 64 bits. So 8 bytes. Yeah, 64 bits divided by 8 bytes. So each offset here is going to be at an increment of 8. And we're going to have many lectures coming up explaining all this in a lot of detail. This is just to give you an overview, an introduction to what we're going to be talking about for the rest of this course. You're going to learn how to ideally be able to actually write code that translates code in a high-level language into machine code that actually executes all these instructions to set up the stack frame for different function calls and whatnot. And to make things easier for you, for your compiler, you only have to support one function per file. So it should be fairly straightforward. Hopefully, it's more straightforward to do that than managing multiple functions. Okay. Oh, I guess, whatever. Yeah. So again, yeah, stack frame, activation record, holds all this information about a function call. So when I have a function in my C code here, like what I can do as an example, if I were to change this example to declare a variable x, and then just return x, the variable x, the memory for it, would actually be located at compile time because it's a static automatically located variable for me. The space for the variable x would be included in the stack frame for the function main. This is different from if I were to call malloc. This would be located on the heap. So if I were to say malloc size of int, this would be located actually on the heap, which is a different part of memory, not the stack. So this would actually be located at runtime. But for our purposes, for the language we're going to be defining, we're not going to have any dynamic memory allocation. We're only going to support local variables, which are going to be on the stack. So if you want to know more of the difference between heap and stack, you can take an OS course, or you can ask me any questions. I won't go into too deep of detail here because we're going to be focusing mostly on stack allocated variables for our compilers. Yeah.
So I got a little lost on this, and I tried looking online. So GCC feeds like the start, like in CRT0, but what is start like from? Like what?
It's just a convention. To be honest,
Is
like
it only for C though, or because I couldn't find it for anything else?
good
besides
question.
C.
I don't know if other languages compile having the start symbol as the underscore start as their entry point symbol. I don't know if other languages do that or not. I just know GCC does it. Yeah.
Okay, so it's just a convention for the language.
Yeah, yeah. I think it's the loader that looks for underscore start specifically.
Because I saw like one thing on Only Go, and it says that you have to like feed your own if it's not C. So
Interesting. Yeah, I mean you could just compile something and then do object dump on it and see, yeah, and check. So
thank you.
What determines if something is put on the stack or in a register? Like if it was constant or static, it would be in the register.
Not necessarily. It depends on. So the registers, there's a finite number of registers that you have available as a programmer, and not all of them are available to you. There are a finite number of registers, and not all of them are available to you as a programmer. Some of them are general purpose. Some of them are meant for specific reasons only. Like I'll go down here to list the list of some of them. Like RBP, for instance, RSP. These registers have specific conventions of what they're supposed to be used for. Now, for what registers, what variables are stored in what registers, that depends on the ABI. The ABI will tell you when to place a variable in a register versus when to place it on the stack.
I don't know if this is related to this class, but what what differentiates CPUs and like how many registers they have? Because I know like I think on default they're like 16, right?
I don't know for sure.
Okay.
Yeah. And there might be the ABI might specify how many registers are available to you as well. I'm not sure. Yeah.
So it's not like a core related thing or anything?
I don't think so.
Okay.
No. Yeah. The computer architecture course would tell you more. Yeah, so I mean, speaking of computer architecture, you all have taken CDA by this point, I think, right? So you know that when a program runs, it just goes into memory, and then you set the program counter to the initial instruction. You start executing from there. So the way we're actually going to be executing instructions or functions in our code, in our assembly code, is actually pretty neat. We just have the call instruction push the address of the next instruction to execute into the stack, and then we just jump to whatever function we're supposed to call, run its code, and then pop off the stack the previous instruction we were supposed to continue execution from. And then RET kind of works in the opposite way, where we just pop off the stack and jump to whatever instruction we had pushed before the last call to the call instruction. We'll see more of this later in the next part of the course. Again, this is just like an introduction, but we'll see like whole lectures on using these two functions. So. Yeah. So. Well, again, we'll see this more in another lecture, but function prologues, epilogues, setting up the function call, putting values in the correct registers, extracting values from registers that they were placed there beforehand, and then epilogue, tearing down the function call. from value. These are all things we're going to see in future lectures, so I don't want to go into them in too much detail. Yeah, so more notes here. Yeah, and yeah, that's it. That's all I have for today. So we ended up a little early. That's fine. I think some of the next lectures will be a little earlier. We'll probably end a little early. I think Sinan and Ryan might end a bit early because we have a lot of lectures that are. We originally were able to fit them in 50 minutes, but we have twice as much time now for this semester, so I might be able to go into more detail on certain topics, which is good. So if you have any questions, please ask me now. Otherwise, have a nice weekend, and I'll see you all next week. Sinan should be going over the exam questions on Monday.